Finally, we get to talk about reinforcement learning techniques that can be applied to problems like blackjack. This will be cool to see, but the bigger picture is even more important. That is, if you face a problem that is easy to simulate and doesn't have too many states and actions, you can learn the optimal strategy. Many problems fall into this category, so this is a big deal, but it'll take focus and patience to understand it. If you're following this 6-part series on reinforcement learning, you already have that. So let's dive into part 3, starting with a short review. If you're too smart for that, skip with the time codes. Otherwise, here goes. In part 1, we said our problem is a finite Markov Decision Process, or MDP. We could think of it as a process whereby an agent takes actions that are passed to an environment, which then produces a reward and the next state. These are then passed back to the agent and the process repeats. In the episodic case, which is our focus, it repeats until some terminal state is reached, marking the end of an episode. The possible state, action, and reward values are restricted to certain problem-specific finite sets. Here, if we include terminal states, we'll call that S+. The dynamics of the environment are given with a probability function, which provides the probability of the next state and reward given the current state and action. I'll call this the MDP distribution function. Our goal is to determine a policy, which is a state-dependent distribution over actions. The agent selects actions by sampling from this distribution. If we run the policy through the MDP, we'll get a trajectory of states, actions, and rewards. We want the gamma discounted sum of future rewards to be high when averaged over many trajectories. That sum is written as GT, which means our goal is this. To achieve that goal, we consider state value functions and action value functions, which are the expected value of GT, assuming the policy pi determines the subsequent actions, and given a particular state or state-action pair. We learned how we can find the optimal policy if we can find the optimum of these functions. Also, when we talk about our estimates of these functions, we will be using these capital letters. In part 2, we covered generalized policy iteration. It refers to any algorithm with the following interweaved processes. First, we initialize some policy and value function. The evaluation process moves the value function towards the policy's value function. The improvement process makes a slightly better policy by using a greedy decision rule over the value function. These two continue until everything stops changing and we must be at the optimum policy and its value function. Got it? If it's not clear, watch the other videos. But otherwise, we can now discuss Monte Carlo methods for RL. A huge difference from the previous video is we do not know the environment dynamics. So we don't get direct access to this. Instead, we merely get samples of trajectories after running some policy through the MDP. To address this, MC uses averages to approximate expected values and GPI to obtain policies approximating the optimal policy. As you'd expect, approximations are the best we can do with finite samples. But I should point out what it doesn't do. MC does not estimate the MDP distribution function and proceed with GPI as though it's known, which is a natural idea, but not what we're doing. In fact, this is good reason to discuss model-free versus model-based methods. And that starts with the definition of a model. In our context, a model is anything the agent uses to predict the environment's response. An example of this would be a direct estimate of the MDP distribution function, as mentioned a second ago. Now, model-based methods are methods where the agent uses a model to plan actions before it takes them. As an example, a chess engine uses predictions of the opponent's moves to determine its best move before making it. Next, model-free methods are methods without a model. They merely learn associations between actions and high rewards, and that's all we technically need. Okay, so Monte Carlo methods are model-free. This makes them simple and relatively easy to tune, but it also means we need to estimate action values instead of state values. Why, you may ask? Because we need a model to connect actions to states. To see this, say we did in fact estimate V, the state value function. In that case, if we'd like to pick the max value action, we'd still need to form our estimate of Q, since that's what's used to evaluate actions. That means we'd have to construct this. But here's the problem. Because it's model-free, we don't have this. So this means if we're going to have to construct an estimate to Q, we might as well estimate it directly. All right, Now we can get back to it, starting with Monte Carlo evaluation. Our goal is, given trajectory samples under the policy pi, estimate its action value function Q. And now, I need to do something I hate, say something confusing. Just a second ago, I said we need to estimate Q from model-free MC, and that's 100% true. But when we do evaluation only, we can express our Q estimation procedure as a V estimation procedure. We can see that by imagining a new problem where the new states are the state action pairs of the given problem. From this perspective, any evaluation algorithm estimating V of this new state would be estimating Q of the given problem. What's happening is, since evaluation treats the policy as a fixed object, we can consider the policy as part of the environment and pretend there's no policy and proceed with value estimation. This is useful for two reasons. The first is it's a generalization of what you might read. If you come across a state value estimation method, you'll know it can be used for action value estimation. In fact, you'll need to think that way very shortly. The second reason is it simplifies our analysis a bit. In particular, it means we may instead study a Markov reward process, which is an MDP without actions, and has trajectories like this: SR, 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 until termination. This means our data is M trajectory samples of an MRP. We can write one trajectory sample like this, where little m indexes from 1 to capital M. If you're also reading from the textbook, this is a little deviation from their notation. Okay, and that brings us to the main idea of MC. Use averages to approximate the policy's value function. Remember, the value of state S is the expected return when the state at time t is S. The idea is to approximate it with this. This is just the return averaged over all times S was visited in the data. Let's break it down. First, we're summing over all trajectories and each time step within those trajectories. This indicator selects out state S, the state whose value we're trying to calculate. This is the sample return at time tau from the mth trajectory. And that means this whole thing is the sum of all returns in the data that followed state S. Finally, CS just counts how many times state S was visited, and that gives us our estimate, VS. But there's an issue. To calculate this, we must process a batch of M trajectories. What would be better is if we applied an update rule after each trajectory, like this. Applying this is in fact exactly the same as calculating the average up to the mth sample. Here, C of SMT counts all visits to the state up to time t of the mth trajectory. Now, if we were to plot this for one state over the episode index M, then we'd get something similar to this, which basically means we make smaller updates after we've processed more data. That makes sense, but we can actually change this to a constant between 0 and 1, and we'll still converge to the right answer. This is simpler to study, so we'll do that. That means we can change our update rule to this, where alpha is a constant we need to specify up front. This is called constant alpha MC, and alpha is called the step size. Let's get familiar with its behavior. Here, I have the episode index M, and over here, I'll be showing our constant alpha. Let's say the true value for some state S is this. Next, if we assume, just for explanation's sake, that state S is visited exactly once per episode, we can plot the returns. Now, using an alpha of 0.2 and applying the update rule after each trajectory gives us this. This is our estimate of state S's value as we process trajectories. As you can see, eventually converges approximately to the truth. Also, we can see the effect of alpha. If it's small, then the estimate takes a while to catch up to the right place, but it's accurate when it gets there. If it's large, the estimate gets to the right area quickly, but it's a noisier estimate. In general, the best choice of alpha will be problem dependent. All right, it's about time we do a multi-state example. This is example 6.2 from Sutton and Barto. We'll be looking at a Markov reward process with 7 states, 2 of which are terminal. All rewards are 0 except when transitioning to the upper terminal state, in which case it's 1. Also, no discounting. The initial state will be the center, and each transition is a 50-50 chance of going up or down. So one episode looks like this. and another. You get it. Now to apply constant alpha MC, we start by declaring, based on nothing, that alpha is 0.05. Next, we need to create our VS table, which we can picture like this. These are the states, and the vertical axis will tell us the table values. The algorithm starts by initializing all non-terminal state values to 1/2, though you can pick anything. In this case, it turns out you can interpret the values as probabilities, so 1/2 is a natural choice. Okay, now we sample one trajectory and apply our update rule. Okay, now if we sampled another episode, we'd get another update to the state values. And as you can imagine, the complete algorithm involves many updates over many episodes. In the end, it just bounces around the true values. So this approach works, but let's measure it. Let's look at the distance between our estimates and the true value and create a new plot. The horizontal axis will be the number of episodes we've processed, and the vertical axis will be the absolute difference averaged across the states. Now, I'll show you how things evolve with an alpha of 0.02 and if we process 30 episodes per second. This shows us how long convergence takes and provides another view of alpha. If we set it to 0.03, we'll see this. We more quickly get to an appropriate answer, but it bounces around more once we're there. If we set it to 0.01, we'll be slow to arrive at our answer, but it'll be a better estimate once we're there. This is just another view of alpha's quick and noisy versus slow and accurate trade-off. And now, finally, we're ready to move on to Monte Carlo control. Since we'll be changing the policy, we can't study a Markov reward process anymore. So let's ask, what Markov decision process might this process be a simplification of? The obvious one I can think of is to say it's a deterministic environment with up or down actions, and the policy is 50-50 up or down. So the state value algorithm we just covered was actually equivalent to applying this update rule. Applying this would give, for all state action pairs, action value estimates. This is our Q table. Now we can ask what policy improvement looks like. That is, how could we improve upon our 50-50 policy? Well, as we learned, we argmax over actions in each state, and that gives us the optimal path, which always achieves a value of 1. Nice. But now I'm going to present a treacherous issue. What if our problem had included this state and the transition to it yields a value of 2? Now what? Well, the policy learned by the agent is still to go up. That's because the agent learned with the up or down policy and knows nothing about going right. It's like we're missing entries in our Q table because we never tried them. This is a devastating problem for RL. It's called the Exploration-Exploitation Trade-Off. It says that to discover optimal policies, we must explore all state action pairs. But that trades off with getting high returns, where we must exploit the state action pairs we already know to be high value. The question is, how do we weigh these two? Well, it appears there are no great answers. It's very much an open question. Here, we'll consider the simplest approach. First, let's pretend we have infinite data. In that case, we can at least guarantee that the optimal policy is always discoverable if our policy is soft. That means it gives a positive probability for all actions in all states. This guarantees that in the limit, all state action pairs are visited infinitely often, and GPI will be able to find the optimal policy. So, what would a good soft policy look like? Well, intuitively, it would start with a lot of exploratory actions, and then, as the data rolls in, explore less and exploit more. But we're going to consider something much simpler: epsilon greedy policies of the action value table. These say, with some small probability epsilon, take an action selected uniformly from all possible actions. Otherwise, select the max action value. Basically, we're sprinkling in some random exploratory behavior, and how much we do is controlled with epsilon. And so this is how we do MC control. MC evaluation updates the value of the Q table, and MC control tells us how to use it to select actions. And we've done so with a very crude approach to the exploration-exploitation trade-off. Not too complicated. But wait, we don't have infinite data. Yes, and actually, that doesn't change our approach. We simply accept that we'll settle for whatever approximately optimal policy we landed on once we reach the limit of our data. There's not much else you can do. Okay, so at this point, you've seen the components, but they haven't been collected into a single algorithm that accomplishes our task: obtain an approximately optimal policy with mere samples. So let's do that finally with the blackjack example from Sutton and Barto's book. In this version of blackjack, we have an infinite deck with 13 cards where the suits don't matter. Each card has a numeric value, except the ace can count as either 1 or 11, whichever helps more. The game begins with 2 face-up cards for the player and 2 cards for the dealer, one face down. The goal is to have the sum of the player's cards closer to 21 than that of the dealer without exceeding it. To do that, the player can hit, meaning receive another card, until he either sticks and he's happy with his sum, or he goes bust, in which case his sum exceeds 21 and the dealer wins. If this stops with him getting 21 exactly, that's blackjack and the player wins. Otherwise, it's the dealer's turn. The dealer follows a very simple rule. First, she reveals her face down card. Then, she hits until her sum exceeds 16. If the dealer goes bust, the player wins. Otherwise, their respective sums determine win, lose, or draw. So that's the game, and it's not too hard to simulate as an MDP. The agent is the player, and the state, it turns out, is a combination of 3 things: the dealer's one shown card, the agent's current sum, and whether the agent has a usable ace. A usable ace is an ace which can count as 11 without going bust. It turns out this makes for 200 possible states, and it's a good state definition because it's everything that can matter when selecting the action of hit or stick. The rewards are undiscounted values 1, 0, or -1, depending on whether the agent wins, draws, or loses. Now finally, we can talk about the algorithm, starting with Q, which represents all state action pairs. That's a 4-dimensional space, so we'll need to get creative visually. Well, there's nothing more creative than a grid. Each grid row will refer to one of our actions, either hit or stick, and each column will refer to whether there is not a usable ace or is a usable ace. We can represent the remaining 2 dimensions with heat maps, where this is the agent's sum and this is the dealer's card. Here I'm initializing everything to 0, and I've highlighted the max action values with green outlines. At the start, stick and hit are tied everywhere, so we arbitrarily select stick. Now, our goal is to update these to give the action values of the optimal policy, and that will in turn tell us the actions of the optimal policy. So let's discuss the algorithm. Now, there are several possible implementations, and this one isn't particularly efficient. So just try to understand the component operations and how they work together generally. Okay, before it begins, we must provide 3 inputs: epsilon, the probability of taking an exploratory random action; alpha, which is the step size; and m, which is the total number of episodes we will process. Pre-specifying the number of episodes just simplifies the explanation. More typically, we process episodes until values stop changing. Okay, then we initialize with some epsilon soft policy and our Q table with some number or numbers. I've already done that with 0. Next, we loop m times. For each, we will use the current policy to sample a trajectory. Then for each time step within that trajectory, we will calculate the return, and for the state action pair at that time, we will apply the update rule to the Q table. Finally, we update our policy to be epsilon greedy with respect to our Q table. Okay, I'm hiding things a bit with this notation. The actual algorithmic details are here if you're curious, but it's just doing what I said. Okay, so that's it. After this is done, Pi should at least approximate the optimal policy. Let's give it a shot. I'll set epsilon to 0.1, alpha to 1 over 5,000, and m to 10 million, which yes, is quite a lot. RL can be obnoxiously needy. Okay, now I'll show how these values evolve as we process a different number of episodes per second, starting small and then increasing. Here goes. Very interesting. The most important thing is we have approximated the optimal policy. The true optimal policy is this. So we're close. I'd say the algorithm works. But let's make some observations. First, we have more samples in spots where our policy goes, and those spots have better estimates. For example, here corresponds to hitting when you have a sum of 21 already and no usable ace. Intuitively, we know that value should be -1, yet these numbers aren't close to that. To understand this, let's look at action values of the same state as we process episodes. We see that the optimal action is clear very early on, so the algorithm doesn't waste samples on improving the estimates. But let's also look at where our algorithm made a mistake. Here, we get to the correct general region quickly, but there's enough randomness that we ultimately make the wrong choice. To me, this says that hitting and sticking have similar enough effects that we'd need a smaller step size and probably more samples to really split the difference among the noise. We're right on the border of the optimal policy, so that's not too surprising. Now, for a different error, we didn't get enough samples to even plateau off, and that's because this corresponds to the usable ace case, which is observed less frequently. And before we get to that plateau, it's hard to determine the right action. More specifically, most rewards are -1 from this state for both actions, so the update is very correlated across those actions. The update only uncorrelates once we're in the right region and the policy has matured, so it's important to get there fast. In fact, if we reran this with a larger step size, we'd get the right answer. Overall, these mistakes tell me that this constant alpha approach really is more simple than it should be. Different state action pairs require different things, and that partially explains why RL methods can be so sophisticated. By the way, if you find this interesting, I've included a link in the description to the Python code that does this, so feel free to check it out. Okay, but now we're in a great spot to briefly cover one other hugely important topic: off-policy methods. Off-policy methods are a generalization of what we've already been doing, which are on-policy methods. To understand them, we need to understand that our policy was actually playing two roles. Here, it's used to generate the data, and here it's updated so it can be returned as a near optimal policy. In off-policy methods, these roles are separated. To do so, we'll need to tweak our notation a bit. The behavior policy is used to generate the data, and we can refer to it as B. The target policy is the policy we'd like to iteratively improve and evaluate so it can approximate the optimal policy. We'll refer to this with the same notation we've been using, pi. Now for on-policy methods, the behavior and target policies are the same. For off-policy methods, the behavior and target policies are different. And that's a huge deal. Just imagine you're on the job, ready to unleash some diabolical RL. Naturally, you'll start with whatever data is available. But if you're only familiar with on-policy methods, you'll realize you have to immediately throw it all out because the data wasn't generated according to some policy iteration strategy you are yet to create. Well, that's ridiculous. You'd like to use that data, and that's where off-policy methods come in. So let's discuss the off-policy adjustments we need to make to our previous algorithm. First, we recognize we want the action value, which is the expected return from taking action A at state S under our target policy going forward. However, our data is under B. So, without any adjustments, we'd be estimating the expected return under B. So what do we do? Well, we recall importance sampling, which I actually have a separate video for. Basically, it enables estimating an expectation of one distribution using samples from another. In our case, that means we use this. This says that the thing we're after is the expectation under B of the return multiplied by the ratio of the probabilities of that return under the two policies. We will label this ratio as rho. It turns out it is equal to just the product of the ratios of the two policies over the remainder of the trajectory. Next, we require coverage, which means if the target policy might take a specific action in a particular state, then so must the behavior policy. It ensures, in the limit of infinite data, we won't have zero data in places where the target policy might end up. With that, we can discuss one way to adjust our previous algorithm to be off policy. It looks like this. I'll walk through the differences, but I should mention, for explanation purposes, it's designed to be similar to the previous algorithm. So, it won't handle a data dump given to you, but it's a short leap to get there. Okay, first, the behavior policy is now something we need to provide up front. Second, the target policy no longer needs to be epsilon soft, since the behavior policy can handle exploration. In fact, for simplicity, we'll restrict the target policy to be deterministic. Okay, next, we sample an episode using the behavior policy. Within each time step, we form the product of policy ratios so we can use it as a multiplier on the return. Beyond that, there's no change to the update rule. Finally, our policy improvement is much simpler. The action is just the action of the highest value. And now we can see it in action. Let's run through the same animation we saw earlier using a behavior policy with a 50-50 chance of hitting or sticking. Here goes. And we've done it. This time with fewer mistakes. Not exactly sure why it did better. What I can point out is that we are better estimating state values the target policy isn't even close to considering. And that's not necessarily a good thing. And this brings me to one huge caveat we need to know about off-policy methods. They could be much higher variance, especially with the rather naive algorithm I showed. That means, all else equal, you should expect the estimates to be worse in regions where the target policy expects to be. That's because off-policy methods waste samples in other places. There are ways to alleviate this that I'm not covering, and those will be must-dos if you're applying this stuff yourself. Also, these issues will be especially difficult if you have a huge table to estimate, in which case this whole approach may fall apart. Now that I've said that, I'm free of all responsibility if these methods don't work for you. But with that, we're done with part 3. You now know a little chunk of reinforcement learning, but certainly not that much. You're missing something huge, temporal difference methods, and there's only one way to solve that. Watch my next video. I'll see you there.